Mass spectrometry. Have you got it? This short video quiz assesses your understanding of the general processes involved in electron impact mass spectrometry and your understanding of the three principal pieces of information provided by a mass spectrum, including molecular mass, evidence of certain common elements by their isotopic signatures, and implications for structure from fragmentation patterns. This quiz consists of 3 questions. It's meant to be taken after you have studied the material and think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. Number 1, fill in the blanks below. Some of the answers are started for you. In an electron impact mass spectrometer, an intense beam of electrons is fired at a vaporized sample dispersed within a vacuum chamber at low concentration. The impact is so strong that an electron is knocked out of the gaseous molecules, producing a very high energy radical cation, the molecular ion. This ion is produced with enough internal energy to break bonds. While it is possible that this ion will survive to be detected, after a few vibrations, it is quite likely that this ion will spontaneously blow apart, fragmenting into 2 pieces, a radical and a cation. The radical is lost, but the cation, being charged and taking a curved path through the spectrometer, depending upon both its mass and its charge, can be detected at a target. This is because when the ion hits the target, it will take on an electron, and that amounts to producing a tiny electrical current. It is this tiny current that is detected. By scanning rapidly, several times per second, through a set of magnetic field strengths, specific masses can be selected to hit the target. It is these pings on the target that then are counted by the software and displayed as a mass spectrum, usually in the millions or tens of millions of counts. The tallest line on this histogram is the one with the most counts and is called the base. It represents the most probable fragment mass. Fill in the blanks below. Pause the video while you answer this question. Okay. It is important to understand that the measurements of a mass spectrometer are not average mass. They are made for individual ions containing specific isotopes of any given element. Since different isotopes of the same element have different masses and predictable natural abundances, fragments and the molecular ion will show predictable count ratios. 2 common halogens, bromine and chlorine, particularly recognizable naturally abundant isotope ratios. So, for example, on the spectrum on the left, we can pretty much instantly know that this structure must contain 1 Br, and on the spectrum on the right, 1 Cl. Notice that we see this 50-50 ratio of a mass and its mass plus 2 value. For example, 135 and 137, 107 and 109. In addition to that, we should be able to see a mass, a fragment, that represents the loss of that bromine or chlorine. And the way we can find this, because bromine is 79 Br, 50%, and 81 Br, 50%, we should be able to find a fragment which is exactly 79 less than one of the mass ion peaks and 81 less than the other. Okay, likewise for chlorine, we see this 3-to-1 ratio, and that's because chlorine is 75% Cl35 and 25% Cl37. And so we also should be able to see a peak that's 35 less than the smaller of these and 37 less than the other one. And that in this case would be 56, and indeed we see that 56. Okay, here's a challenge. Match the two structures, A and B on the left, to the two mass spectra on the right. Indicate fragment masses using the Z-line description shown on the right, where we indicate a fragment by drawing a line through the bond, and then on either end of the line, we indicate the mass of that piece of the molecule. I know the writing on these spectra is a little bit small, so I've added M over Z values of the prominent peaks up at the top, 15, 27, 43, etc. You don't have to try to read those little tiny numbers. And in addition, some common element and fragment masses are given below. For example, CH3 is 15, C2H5 is 29, CO is 28, CO2 is 44. Okay, see if you can figure out what it is in these spectra that differentiate compound A from B. Do not try to understand the entire mass spectrum. That will not be possible. But you're looking for differences and differences that might be able to be interpreted. I would start by drawing the little lines I'm talking about, fragmenting the various bonds, and seeing what kind of numbers you get. Okay, so pause the video, take your time, see what you can figure out. Okay, well, let's see what we have here. I can cut molecule A at these three places for sure. The one on the right is methyl at 15, and if I subtract 15 from 102, I get 87. And the one between the carbonyl group and the oxygen, well, the oxygen is 16, so that's 16 plus 15 is 31. And on the other one, we're subtracting 16 off that 87, so that's 71. Okay, and then carbonyl CO is 28. So if we add that into our chunk on the right, that gives us 31 plus 28 is 59. And subtracting that from 71 gets us 43. Okay, how about this one over here? We'll chop this isopropyl group off. That's a C3H7, so that's 43. And that leaves us with 59, which is on both spectra. Add in another 16 for that oxygen to this 43, and that gives us another 59. And that must mean that we're also leaving 43. So there's two ways we can get 59 and 43. And that's pretty much it for that molecule. All right. So looking at these, the big distinction here is this 71, I think, on the left. Only the spectrum below has the 71. There's nothing of that in the top spectrum. And just to point out that what we've done is we've taken off 31 from 102 to get 71. Now we don't see 31 per se. I mean, I suppose this tiny thing, but that won't count. That's okay, because we can often see just one of the two possible fragments with the cation. All right, so all the other numbers, 43, 59, are in both spectra. It really doesn't help. The 8715 is basically there in both of them. It's just this very specific 71 right here. Key difference between. So we conclude that this special peak of 71 indicates that it must be the first structure, A, and that leaves B to be this first structure. All right, so remember, electron impact mass spectrometry involves the odd situation of when the impact is so energetic that it actually kicks out an electron from the molecule. We say that the molecule is ionized. The molecular ion produced can be detected because it is charged. The masses detected are for specific molecules having specific isotopes. Bromine and chlorine, in particular, have recognizable peak ratios for M and M plus 2 because they each have two isotopes with significant natural abundance. Besides that, the radical cation formed has so much extra energy it generally blows apart, breaks one bond, producing two fragments, a cation and a radical. Of these, only the cation is detected. Which particular bond happens to break is based on probability, involving many factors. The mass spectrum is a histogram describing these probabilities. The base peak generally indicates the mass of the most probable cation fragment. Remember, especially if we have two structures to compare, we can sometimes decide between them based on which has the best fit of possible fragments to what we see in the spectrum. And while it's possible and sometimes necessary to determine a structure directly from mass spectrometry, usually this analysis is in connection with proton and C13 NMR and IR data. And one final point, really don't obsess over the mass spec data. You will never be able to understand all of the peaks, even some of the larger peaks, because there are many processes that make these fragmentations. And we are not in a position at this point in this course to understand or dig any deeper into this than the basic simple fragmentations like loss of a methyl group or loss of an ethyl group or a carbonyl group being split off from a molecule. All right, so I hope that helps, and I hope you've got it.